The first official reaction mechanism covered in most organic chemistry courses is the Sn1 reaction. The overall reaction is highlighted by a functional bit of a molecule transforming. Understanding the rationale behind why this reaction proceeds as it does is of utmost importance when beginning the journey through organic chemistry, as the fundamental concepts of this reaction contain ideas that are repeated throughout the subject. This reaction does not proceed in a single step. That is, a hydrogen chloride molecule doesn't just swap parts to make the product. Instead, the reaction proceeds in several discrete steps. The mechanism for this reaction begins with protonating the oxygen in the alcohol with hydrogen chloride, forming a positively charged oxonium intermediate. This step can be classified as an acid-base reaction step. This intermediate then dissociates to form a positively charged alkyl chain, called a carbocation, and water as a byproduct. Consider the molecules that we have at this point. There's water, a carbocation, and a negatively charged chloride ion. Electrostatics predicts that the chloride ion and the carbocation will move toward each other, and that's exactly what happens. In this final step, a new covalent bond is formed between the chloride ion and the carbocation. Putting this all together, we see how these individual steps combine to form the reaction initially presented. Now that the basics of the mechanism have been covered, let's talk about the nomenclature used to describe it. A nucleophile is a species that is attracted to positive charges, that is, nuclei, and these molecules have lone pairs of electrons and are typically neutral or negatively charged. A carbocation is a general term for a molecule that has a positively charged carbon, formed in the second step of the reaction mechanism presented. The stability of this carbocation is important in analyzing this reaction mechanism. Carbocations are classified based on how many alkyl groups are attached to the carbon. Tertiary are the most stable, while methyl are the least stable. Higher substituted carbocations are stabler due to the electron-releasing nature of alkyl groups, which lessen the magnitude of the positive charge. Sn1 chemistry happens almost exclusively with molecules that can form secondary or tertiary carbocations, as less substituted carbocations are too unstable. Another aspect of carbocations is their shape. Carbocations are flat, an important detail for the upcoming discussion. A leaving group describes exactly what you think it would. It is the part of the molecule that leaves during a reaction step. Like the carbocation, the stability of the leaving group is important. The stabler the group after leaving, the better. Transition states describe what bonds are being broken and formed in a reaction step. Between each step in a reaction mechanism lies a transition state. These transition states are highly unstable, so when a molecule is in a transition state, it very quickly relaxes to a lower energy state. If you were to plot the energy of a reaction as it proceeds, the peaks in the plot would correspond to the transition states of the reaction. Each mechanism has a rate-determining step. This step is the part of the reaction that is highest in energy. We care about the rate-determining step because the rate of the reaction is determined by the concentrations of the species involved in the step. In the case of Sn1, the rate-determining step is the formation of the carbocation. This allows us to finally understand the name Sn1. Nucleophilic substitution is occurring with a unimolecular rate-determining step. Another important consideration of Sn1 chemistry is the fact that carbocations can rearrange. When secondary carbocations are formed and conditions permit, a carbocation rearrangement can occur, resulting in a more stable tertiary carbocation. This can happen in two different ways, with a hydride shift or with a methyl shift. Carbocation rearrangements occur very quickly after the initial carbocation is formed. The quality of a leaving group determines whether or not an Sn1 reaction will occur. In this reaction, the hydroxyl is not stable enough to be ejected on its own, but after it is protonated, it is perfectly able to leave as water. Groups like tosylates, halides, and protonated alcohols are typically good leaving groups. An important factor to consider when analyzing the quality of a leaving group is the group's ability to stabilize a charge, if applicable. Tosylates are especially good at stabilizing the negative charge that they are left with. The Sn1 reaction covered in detail so far is by no means the only example of Sn1 chemistry. Since a tertiary alkyl halide can dissolve to reform a carbocation, Alkyl halides can be used as starting materials for other substitutions. They can transform to azides, nitriles, back to alcohols, esters, ethers, and more. If the starting material in an Sn1 reaction is chiral, the product will be a partially racemic mixture. This is because the approach of the nucleophile can occur from either side of the flat carbocation, meaning that both enantiomers can form, although the side opposite the leaving group is favored.